All right, hello everyone. Welcome to our next day of class. We are continuing our discussion of two variable and three variable functions. Last time we looked at what it means for a function to be continuous, and we're going to sort of continue along that theme today, but we're doing the natural next thing to do after beginning to introduce continuity in calculus. The next thing we're going to introduce is this notion of smoothness or differentiability and what exactly that means. So what is differentiability? What are derivatives? Well, it's the same thing that we usually think about. If you have a two-variable function, f(x, y) equals z, then, and we looked at some examples of these two-dimensional functions, or these two-variable functions before. For example, we could have that f is the heat on a surface with the coordinates x and y. So one question we can ask is, okay, well, how quickly is f changing? What is the rate of change of x and y? But that's a bit of a bad question to ask. And the reason that's a bad question to ask is because it's not clear what we mean by rate of change. I mean, after all, what's changing? Is x changing? Is y changing? And maybe this thing increases as x grows, but decreases as y grows. So you need to figure out what exactly we mean when we're talking about a rate of change. What is it a rate of change with respect to? And for that, we introduce this notion of what's called partial differentiation. So if we think about, for example, what's going on with f of x, y, and we want to figure out how f of x, y, what do? We fix a point. We're going to call that point AB. And it's the same story as usual. We're going to fix this point AB, and we're going to say that x is changing. Well, if x is changing, then that means that y is not changing. So we're going to fix y. Y is always going to be b. Well, then what are we really interested in? We're really interested in how the function f(x_b) is changing, where b is constant, x is varying. So we look at how f(x_b) changes. And we give this thing a name. We call it the partial derivative of f with respect to x at the point AB. And that's just the regular derivative we're always used to. We just to remind everyone what we mean when we talk about derivatives, this is just the regular old, limit definition of a derivative. G of a plus delta x minus g of a over delta x over small change in x. That we remember is just all that represents is a very small change in g, or in this case in f, with respect to x. And then we let that change in x, that delta x, go to 0. That's the derivative. That's the same derivative that we always looked at. And it's the same story with y. If we want to look at how y is changing, or rather, if we want to look at how f(x_y) is changing as y changes, but not x, well, then we're going to do the opposite. We're going to fix x equals a at our point, and then look at how f(a_y) changes with y. And this is the partial derivative of f with respect to y at this point AB. And on you go. And it's the same exact process. In this case, you're taking the limit definition in the y-coordinate instead of the x-coordinate, but it's the same basic idea. So these are how we define the partial derivatives of f. So the partial derivative with respect to x is the limit as the change in x goes to 0 of f of x plus delta x, y, minus f(x_y) over x. And there's an analogous definition for the partial derivative of f with respect to y. Now, there are a couple different pieces of notation we're introducing here. We can either say that the partial derivative with respect to x can be written as f sub x, and by the way, a little bit of vocabulary here. That's f sub x, not f of x. So let me just make a little note of that. This would be read as f sub x, but it's not the same thing as saying f of x. F of x would mean f evaluated at x, but that's not what's going on here because f is a two-variable function. So you can either say f sub x of fy, or maybe just fx of xy is okay too. And then you have that's equal to, or that's also written as del x. This weird curly d thing is called either del or delta or partial. And what that means is you're differentiating f partially with respect to x. And basically the operators d dx and del x, pardon me, Basically, they do the exact same thing. They mean the exact same operation. The only thing is that del x explicitly indicates that we're working with a multivariate function. So you wouldn't use ddx with a multivariable function. You would only really use del x with a multivariable function. And there's analogous notation for the partial derivative of f with respect to y. In this case, you're going to take f sub y, or del f del y, or del z del y, and it's the exact same formula. Now, if you're looking at these things, then it can sort of seem like, well, gee, okay, but I mean, calculating these limit definitions of derivatives, I remember that being kind of difficult. That was kind of frustrating. Are we going to have to do that? Well, no, we're not going to have to do that. We're not going to have to calculate limits explicitly, and the reason we're not is because if you stare at that for a second, you might recognize, oh, wait a minute, let's look at the partial derivative with respect to x. So right now, we're just going to take a quick look really at just the partial derivative with respect to x over here. And the only thing that's changing is the x coordinate. The y coordinate is staying the same, right? The y coordinate isn't changing, only the x coordinate is changing. What that means is that y is constant. So you can differentiate this thing as if y were a constant. So when you're actually going to go calculate something like this, then let's see what that looks like if we actually calculate one of these things. Well, okay, we're defining fxy as x cubed plus x squared y cubed minus 2y squared. So you can differentiate this thing as if y were a constant. So let's take a look here. Del x of x cubed plus del x squared y cubed plus del x negative 2y squared. Now you're doing this thing. Now what about del x of x cubed? Well, that's just the derivative of x, but with respect to x of x cubed. We know what that is. That's 3x squared. Easy enough. And then meanwhile, you've got del x of x squared y cubed. Well, y is a constant, so y cubed is a constant. And if y cubed is a constant, then you just leave it where it is. So that's plus 2x y cubed. And that just leaves the last term, del x of negative 2y squared. But again, y is constant. So if y is constant, then negative 2y squared is constant, so that just becomes del x of 0. So plus 0. Whole thing comes out to 3x squared plus 2x y cubed. That's our final answer. There's our final answer for what that partial derivative is. Now you can do the same thing with fy. In this case, the first term, del y of x cubed, that's 0 because x is constant now. Y, again, x is constant, so you differentiate x squared y cubed with respect to y. You differentiate the y cubed, but the x squared is constant, so that becomes 3x squared y squared minus 4y, or to be a little more concise, 3x squared y squared minus 4y. Now what happens if you evaluate those things? You can actually, you can talk about derivatives at specific points, so what would that be? Can someone tell me what fx of 2, 1 is? Let's see if we're following along here. And after a little bit, we might notice that what this is, oh, sorry, wait a second. And move some things around. But basically what's going to happen here, let me go back to drawing this thing. So you plug into 1 into that, 3 times 4, so 12 plus 4. So the first one becomes 16. The next one, f of fy to 1. Again, 3x squared y squared, so that's going to become 12 minus 4, so fy to 1 is 8. That's about it. That's really all there is to it, just plugging and chugging, and the same that we always do. All right, so what exactly are these things? Well, you can think about fxab and fyab as slopes of a tangent line. What tangent line? Well, specifically we mean that fxab is a slope of the tangent line to the trace of the curve, or the trace of the surface, fxy equals z, in the plane y equals b. Now, that's a lot of words, but we can unpack what that means. Basically, a surface in three-dimensional space doesn't really have a slope. It doesn't really have a tangent line, nor does a curve in three-dimensional space. But you can talk about a curve in a specific plane, a vertical plane, and talk about the rate of change, the slope in that plane. And what does that look like? Well, let's take fxy equals 4 minus x squared minus 2y squared. Well, you differentiate with respect to x, you get negative 2x. So fx11, well, that's just negative 2. So what we see here in this figure on the left, y is constant. Y is always going to be 1, or supposed to always be 1 in this figure. And what that really tells you in this case is this line has a slope of negative 2. And we know that's negative because if you look, here's where the positive x portion is. It's positive x and it's positive z, so the thing is flipped. So it's actually sloping downward, and it's with a slope of negative 2. Likewise, on the right-hand side, we've got fy11. That's negative 4. The slope is decreasing with negative 4. In this case, x is being held constant, and y is what's changing. So that's what we mean when we talk about these two tangent lines being, basically being like slopes. You can think about these partial derivatives as being slopes to the graph at that particular point, kind of, sort of, assuming you're working in an appropriate plane. We can keep on going. Let's do a few more examples of this. Let's look at fxy of sine x over 1 plus y. Going through this object, what do we get? Well, you differentiate with respect to x. You need to use the chain rule here because you've got a function of x inside the thing, and that derivative is going to be 1 over 1 plus y times the derivative of the outside, cosine of the inside again, x over 1 plus y. And meanwhile, you have the, meanwhile you've got fy. Again, you need to use the chain rule. And in this case, the chain rule is going to give you negative x over 1 plus y. Oops, sorry, messed that up. 1 plus y all squared cosine of x over 1 plus y. And that's the partial derivative of this thing with respect to y. And you can go all day. You can keep on taking derivatives and partial derivatives of multivariable functions as much as you could possibly want. Now, we also have something called implicit differentiation. Now implicit differentiation this is kind of a funny thing for a lot of students. But basically the idea is you could have a function involving x, y, and z. And if it involves all three of x, y, and z, and you're told that z is a function of x and y, you've been told that explicitly, well, it may not be so obvious how, what exactly that function is. But that's okay. It's not supposed to be obvious what that function is. It's implicitly a function of x and y. So in this case, you've got that z is implicitly dependent on x and y, and that implication is given by this formula. So let's take z equals fxy for some f. All right? I don't know what that f is. We're not going to find it. That's not important. To find the partial derivative, del z del x, then we're going to take the derivative of this equation with respect to x on both sides of the equation. So let's see what happens when we do that. We'll take the derivative with respect to both sides. Del x of x cubed plus y cubed plus z cubed plus 6xyz. Okay, let's take the derivative of each piece individually. First of all, you take the derivative with respect to x cubed. And if you take the derivative with respect to x cubed, or excuse me, let me try rephrasing that. You take the derivative of x cubed with respect to x, that's what I meant to say. And that becomes 3x squared. All right, that's not a problem. So far, so good. what about del x y cubed? Now, y, if you're differentiating with respect to x, y is a constant. Y doesn't depend on x. So that goes to 0. That's not a problem. So this term over here is going to go to 0. But then that leaves del x of z cubed. A common mistake is to think that that thing is 0 because it's a different variable. But it's not 0 because z depends on x. In this case, we are assuming that z depends on x. And if z depends on x, z is a function of x, which means z cubed is a function of x. And if z cubed is a function of x, you need to hit that with the chain rule. The derivative of the outside function is 3z squared. The inside function is just z. So that's going to become del z del x. So just this piece individually, let me make this explicit, just this piece individually is going to be 3z squared, derivative of the outside, times derivative of the inside, del z del x. We can't do any better than that because I don't know how exactly del z, I don't know how exactly z depends on x. I just know that those two variables satisfy that equation. Likewise, we can say something about del x of 6xyz. Again, once again, z is a function of x. So here you've got two different functions multiplied together. This is product rule. So for this guy, I'll do it up here so the images don't conflict. This is just going to become 6 to differentiate with respect to just x, and just x is what you're differentiating. Then that just goes away to 1, so it becomes 6yz plus 6xy derivative with respect to z. And that's what we see in this penultimate equation. So down here we get this big equation. And now it's just algebra. We're going to isolate del z del x. And so separating that out is going to give us, you can maybe I should have included this as an extra step, but separating that out, separating this whole thing out, is going to give us del z del x times 3z squared plus 6xy plus 3x squared plus 6yz. That whole thing equals 0. So now it's just algebra. And after the algebra, what you find is you get an explicit formula for del z del x. And you divide it by 3 and simplify it. You finally end up getting del z del x is negative x squared plus 2yz over z squared plus 2xy. So that's the derivative with respect to x. How do we find the derivative with respect to y? Well, it's almost the exact same idea. In this case, you're going to take the derivative of both sides with respect to y. Once again, we have to remember that z is a function of both x and y. So take, for example, x cubed plus y cubed plus z cubed plus 6xyz. That is going to be del y of x cubed plus del y of y cubed plus del y of z cubed plus 6x plus del y of 6xyz. Well, derivative of x cubed with respect to y, while x doesn't depend on y, x is constant, that's 0. So let me just draw this in explicitly. This term over here is 0. This term over here becomes 3y squared, or differentiating with respect to y. Again, we have to hit this with the chain rule, so this once again is going to become 3z squared del z del y. And then hit the last one with the product rule, giving us 6xz plus 6xy del z del y. And that's about it. That's exactly what we see in these in this penultimate equation. And once again, you just do the algebra, and it works out to be del z del y is negative y squared plus 2xz over z squared plus 2xy. So that's our final answer. And by the way, for those of you who haven't done implicit differentiation in a couple years, which is probably many of you, it might be a little bit uncomfortable to see that del z del y includes z as one of the variables. And while I acknowledge the discomfort in that, it's important to keep in mind that, we don't actually know what z is as a function of x and y. This is the best we can do. It's not great, it's not perfect, it doesn't tell us everything, but it tells us how z and y are changing at a particular point. You may get some challenge problems that help you learn a little bit more about what exactly this whole implicit differentiation business means and what exactly it means to, to have these partial derivatives with respect to several different variables. But that will be probably next week is when we'll start looking at those. Now you can do this with functions of several variables also. Unlike limits, the process for differentiating functions of several variables is immediately transferable. And you write it in basically the same way. You can write del w del x is fx, del w del z is fz. In this case, you really are differentiating with respect to z as its own independent variable. And you find, for example, fz in the exact same way. All you're going to do is differentiate f with respect to z while holding both x and y to be constants. That's about the whole story. Now, meanwhile, you could have that fx1 up through xn is a function of n variables, and once again, it's the exact same story. All you're really going to do is differentiate with respect to the ith coordinate, which I'm calling xi, and hold all of the other xj's, all the other coordinates, to be constant. And that's pretty much all there really is to it. So let's do an example of this. We've got the function fxyz equals e to the xy times ln z. So people who are watching this, take a couple seconds to see if you can work out what these partial derivatives are. Remember, all you're going to do is differentiate it with respect to one variable and hold the others to be constant. So can anyone figure out what fx is? What would fx be in this case, differentiating with respect to fx? After staring at that for a little bit, we can sort of begin to see what that would be, right? You would have fxyz equals e to the xy ln z. So you differentiate with respect to x. ln z is still constant because z is constant, but y is also constant, so you bring down y. This becomes y e to the xy ln z. Similarly, if you differentiate with respect to y, you would get xe to the xy ln z. On the other hand, if you differentiate with respect to z, well, e to the xy is going to be constant because x and y are both constant, but ln z gets differentiated, so that becomes e to the xy over z. Those are your partial derivatives in all cases. Okay. So, by the way, one of the things that we did in Calc 1 is we took several derivatives. Well, you don't have to stop at taking single derivatives fxy and or fx and fy. You can also take derivatives of fx with respect to x and fy with respect to y. I mean, those, because indeed fx and fy are themselves functions of x and y. We can look at how they change also. But here you can take what are called mixed partials. So the notation, so in the notation, you have to be a little bit careful, because if you differentiate it with respect to fx twice, you would write that in either as fxx or as del squared x over del x squared. There's nothing wrong there. Same story with y. You can write either fyy or del squared y over del y squared. I'm seeing that is in fact that is a typo in my notes. So let me make a note of that. This should be, sorry, that should be del squared z over del y squared. That's my bad. But the thing is, what if you wanted to differentiate fx with respect to y? You can do that too. There's nothing to say you can't. That becomes fxy. And fxy, you can write that in Leibniz notation, in this del notation, as the derivative with respect to y of del z del x. Now the important thing is, in this case, you differentiate first with respect to x, and then with respect to y, but on the other side you differentiate first with respect to y, and then with respect to x. So in this case, the order flips. But here's something that's perhaps a little surprising. 1 minute. Oh, hold on. Here's the surprising thing. Most of the time, it doesn't matter. So if you take fxy equals x cubed plus x squared y cubed minus 2y squared, we already had written down and solved earlier on in this lecture that fx is 3x squared plus 2xy cubed, and fy is 3x squared y squared minus 4y. So you can take its second order derivatives, fxx, differentiate fx with respect to x, that's going to give you 6x squared plus 2y cubed. Fxy becomes 3x squared plus 2xy cubed. Sorry, I stated that wrong. I've got a window in front of there. You differentiate with respect to y, you're going to get 6xy squared. And also, if you differentiate fy with respect to x, you're also going to get 6xy squared. And then fyy, you differentiate that with respect to y, you get 3x squared, you get 6x squared y minus 4y. I keep reading the wrong thing. But the thing that we should notice here is that fxy and fyx turn out to be the same function. They both turn out to be 6xy squared. Now, that's not coincidental. It turns out that that's always going to be the case. This is what's known as Clause's theorem. If f is continuous on an open disk that contains some point AB, and both the mixed partial derivatives are continuous on that domain D, then the partial derivatives are the same. The mixed partial derivatives are the same at that point. Now, that's a big result. What that means is that for most of the reasonable functions we'll be working with, that will always be true. And indeed, this is reasonable. It's saying that if f is continuous on this disk, and the partial derivatives are continuous, if the partial derivatives are continuous, then they're actually equal to each other. Now, by the way, that means you can take third order derivatives in any order you want as well. So any number of derivatives can be taken in any order. So for example, you could take fxyx, which is the same thing as fxxy, and that's the same thing as fyxx. They're all the same story. So say, for example, you want to find fxyz, and that's sine of 3x plus yz. You want to find the fourth mixed partial, fxxyz. Well, you just differentiate as usual. You take the derivative with respect to x, which is 3 cosine 3x plus yz, after a chain rule. Fxx, another iteration of a very simple chain rule, bring out the constant 3, and again, treating y and z as constants because they are constants. Fxy, same story. And then fxyz, here it gets a little trickier. It gets a little trickier here because now you have to apply the product rule. So this becomes negative 9 cosine 3x plus yz plus 9yz sine 3x plus yz. Product rule because on the one hand you've got the function z, or more specifically negative 9z, and you've also got the function sine of 3x plus yz. And by the way, you can rearrange those derivatives in any order. They will always give you the same function. All right, so now we know a thing or two about what partial derivatives are and what they look like and how to calculate them. But what else can we do with them? Well, it turns out they're very good for finding what are called tangent planes to surfaces. Now, and I can see that that paragraph has an incomplete sentence in it. But the point is, we can find tangent planes to the surface now. Now, these are planes very much like tangent lines to a curve, but instead of a curve and a line, we're looking at a surface and a plane. So these are planes that just barely skim the surface at this point, and just this one point. You can think about it as if you're standing very, 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 very close to this point, it feels like you're living on this plane. Now, the tangent plane to a surface has to contain all lines that are tangent to the plane. Now, even though we talk usually about tangent planes and not tangent lines, you can still have lines that are tangent to the surface. And those lines that are tangent to the surface are going to be all contained in that plane. Now, in particular, what that means is it contains the tangent lines in the plane x equals x naught and y equals y naught. But those tangent lines are going to come from partial derivatives. So what are we trying to do? What we're trying to do right now is we're trying to find the equation of that tangent plane. So to find the equation, then, well, what do we need for any plane? We need a point on the plane and a normal vector. The point on the plane is the easy part. We can just use the point on the surface, x naught, y naught, f x naught, y naught. That's just the point that we're interested in. That's not that hard. Normal vector is a little trickier. We have to find the direction vector, so the tangent lines of those two curves, and take their cross product to find a vector that's orthogonal to both of these lines. Because, I mean, after all, like I said, we know that these two lines are going to be in this curve. Excuse me, I didn't say that correctly. We know that these two lines are going to be in this plane. All we have to do is find out what those lines are, or at least find out what their directions are. Let's say that T1 is the line that you get when fixing y and varying x. So T1 has slope fx, x naught, y naught. Now, in this case, y isn't changing. And since y isn't changing, we know that that coefficient is 0. I mean, the y coefficient is 0 for that vector. But because the slope is fx, x naught, y naught, it follows that we can just set x to be 1 and y to, sorry, x can be just 1, and z, because this is the slope in parallel to the xz plane, z can just be fx, x naught, y naught. Now, the direction vector for v2, or for t2, that's the vector that, sorry, let me try that again. That's the line that is, that's the line that is along with varying y, but not x. And it's the same story. In that case, the x component is not changing, so x is 0. But the slope is fy, x naught, y naught. So in this case, we know that we can say that the vector is going to be 1 fy, x naught, y naught. Point is, you can find the normal vector by crossing these things. And you just take the cross product as you ordinarily would. And here's what you get. You got negative fx, x naught, y naught in the I direction. In the j direction, you're going to get negative fy, x naught, y naught. And the k direction is just 1. So applying all that together, we've got the normal vector, n. The normal vector is negative fx, negative fy, 1. And that's going through the point x naught, y naught, z naught, where we're declaring z naught to be f of x naught, y naught. So the tangent plane to that equation just involves multiplying the normal vector coefficients with x minus x naught, y minus y naught, and z minus z naught as usual. And there you have it. That's what it is. Now, it's a little more common to express this so that z is on its own. So you can express this a little more commonly as the derivative with respect to x of x naught, y naught times x minus x naught. The derivative with respect to y of x naught, y naught times y minus y naught, plus the evaluation at x naught, y naught, so f of x naught, y naught. Now, compare this to a moment for a function of one variable and its tangent line. Well, the tangent line at the point x naught, fx naught has this equation. Y is equal to f prime x naught times x minus x naught plus f x naught. That's it. That's all it really is. And it's the same story. It very much looks like it's talking about the same thing. The derivative times x minus x naught plus the derivative with respect to y times y minus y naught plus the actual evaluation. So let's do the specific example. We'll find the equation of the tangent plane for the elliptic paraboloid z equals 2x plus y, 2x squared plus y squared. Now, again, what are we going to do? This is just a, this is again just a plane. So z, I'm going to do this in blue as is my custom. We already know that z minus z naught is equal to the derivative with respect to x at x naught y naught times x minus x naught plus the derivative with respect to y at x naught y naught times y minus y naught. So what does that give us? Z is equal to, well, I don't know what this derivative is yet. We'll figure that out in a little bit. Del z del x at 1, 1 times x minus 1 plus, again, the derivative of z with respect to y at the point 1, 1 times y minus 1 plus 3. So what's the derivative with respect to x? Well, del z del x, we can just look at that for a second and see that that's going to become 4x, which implies that del z del x 1, 1 is 4. And meanwhile, del z del y is 2y, which implies that del z del y at the point 1, 1 is 2. So the whole thing comes out to z is equal to 4 x minus 1 plus 2 y minus 1 plus 3. Or if you prefer, z equals 4x plus 2y. So minus 4 minus 2 is negative 6 plus 3, so minus 3. All right. Are there any questions so far about how we found either of these tangent planes? So now what's the important point here? Now here are some graphical depictions of that same paraboloid and the tangent plane in this case. And what do we notice? As we zoom in, they get closer and closer together, don't they? The more we zoom in on that point, the more similar they seem to be. So in other words, that function that we found, 4x plus 2y minus 3, that's a pretty good approximation of our function, provided that the point 1, 1 is, provided that we're approximating it near the point 1, 1. So for example, what's near 1, 1? Well, 1.1 and 0.95, that's near 1, 1. And our claim is that's approximately equal to this plane at the point 1.1, 0.95. You plug all those in, you approximately get 3.3. In fact, the actual value of this function is 3.3225. So, okay, we were off by a fact by about by 1/50th. That's pretty good. That's pretty good. So we give that function Lxy a special name. It's called the linearization of that function near that point. And accordingly, this technique of estimating this function fxy near that point is called linear approximation. Now, this technique always works the same way pretty much. Near this point, the surface fxy equals z looks very similar to the tangent plane at that point. So we actually call it that. We call that tangent plane the linearization of fxy. It's the function Lxy whose surface is just the tangent plane at that point. And again, if you're looking at that formula and thinking, well, gee, that looks an awful lot like the tangent plane formula from before, right? You've got the derivative with respect to x naught, y naught times x minus x naught, ditto with y, plus f x naught, y naught. You might be thinking, well, that looks like it's pretty much the same thing. What's the difference? And there isn't really a difference. They're basically the same thing. Only one of them treats it more as a geometric object, and the other one treats it as an actual function. But you can treat them both either way. So what if, for example, we wanted to approximate the value of f 1.1 and negative 0.1? Now here's your function f. F of xy is x e to the xy. Here's what we're not going to do. So here's what we're not going to do. We're not going to actually take 1.1 e to the 1.1 times negative 0.1. And that's the same thing as 1.1 times e to the negative 0.11. No, we are not going to do this. And the reason we're not going to do this is because I don't know what exactly that is. That's going to be hard to work out. We're going to approximate it. And we're going to approximate it using what's called linear approximation. So we're going to linearize instead. And we're going to linearize near the point that's close to 1.1 and negative 0.1. And that point would be 1, 0. We're going to linearize near 1, 0. So we're going to need to know fx. Fx we can see is going to be e to the xy plus xy e to the xy, which tells us in particular that if you take fx of 1, 0, the point near which we're approximating, you're just going to get 1. Oh, sorry. Meanwhile, we have fy is just xy e to the xy. Excuse me, that's not correct. X squared e to the xy, which means fy10 is also 1. So in this case, the linearization is very simple. It would just be z minus f10. Oh, that's the other thing, is I need to actually figure out what f10 is. So before I do this, I'm going to need to know what f10 is, the little thing I forgot. f10, actually take f10, that's just 1, right? 1 times e to the 0, that's just 1. Now we can talk about the linearization. The linearization in this case is going to be f xy is approximately equal to z minus f10. Oh, sorry, I botched that. Let me screw that up 1 second. It's approximately equal to fx at the point 1, 0 times x minus 1 plus fy at the point 1, 0, but this time just times y, plus f10. And that, as it turns out, is just x minus 1, because fx10 is 1, as is fy, so it would just be x minus 1 plus y plus 1. In other words, x plus y. So what we have in that case would be that f of 1.1, negative 0.1, that's approximately equal to 1. That's not a great approximation. It's a kind of a weird approximation, but it's valid. It works out. And the actual value, let me look for a second, see if I can find what the actual value is. And it turns out the actual value of this thing would be the actual value would be f of 1.1 negative 0.1 is approximately it's approximately equal to 0.985. This was not a very good example. I'm looking at this and I'm realizing this is not a particularly good example because the numbers work out more nicely than I wanted them to. But Dr. Roberts will do some better examples in recitation, and there are some very good examples of doing this in the in Stewart as well. So we'll end here for today with our discussion on linear approximation. So thank you everyone for those who tuned in, and if you have not done so already, good luck on the exam, and I will see you all next week. I'll be doing recitations next week. So thank you everyone. Bye-bye.